Okay. It's really a great pleasure to introduce the speaker today because he is a colleague and friend, collaborator, also in the European Astronomical Society. Ignacio Ferreras, the speaker today, studied undergraduate and PhD in Spain. And that did not prevent him, as it does not prevent people from here to go to excellent places afterwards. He went to Oxford for postdoc, ETH, UCL, University College London, and King's College. Impressive places. And he was then offered a lectureship at UCL. And was promoted to senior lecturer and reader. And after that, he decided to go to his home country, and like several of us did.
Yeah.
And he did not regret it. So that's very important. So today, Ignacio, I will not say a lot more about his work. Whoever is interested, some of you have already talked to him. I'm really eager to hear his talk because I know that inverse problems in physics are very difficult problems. And this, if the speaker says it's a tricky inverse problem, means it's very interesting. Thank you.
Thanks, Nick. It's an absolute pleasure to be here. It's thanks so much for the invitation to come here to speak with you. So let me I'll just put this to check time to make sure that I don't go. So as Nick is saying, there are many times in science, not only in physics, there are many times that we have an inverse problem. Basically, we have some observations, we have some models, and we need to turn the crank backwards to try to see what are the driving parameters. What is the fundamental physics that determines what we are trying to see? So here, as you can see in this diagram, basically present a galaxy. You take a spectrum of it. So in principle, aside from polarization, that I know many people here are sensitive to polarization as well, but I would say aside from that, if you have the flux as a function of energy, that's pretty much all you can get from the galaxy. So the question is, how much can you get out of it? And my talk will be a bit unconventional because I am not simply comparing with the models. I mean, that's in a way what the vast majority of people are doing. You just have your observations, you have your models, you compare, you do some statistical analysis for that, and then you just basically make a deduction on that. So before I start, I already put my, let me see, I'll just put here. I already put this slide, but just as an advertisement for those of you who are interested in these are relatively small textbooks, but they can be used for teaching or for the students. I think they should be quite useful. They are absolutely free to download. It's open source, so you can actually get this, and I hope they can be a bit useful for you. So let's get into this. So the main idea, well, here, let's see if I can get rid of this. Say, okay, I'll just try to move. Okay, I'll try to see if this can high floating medium controls. Okay, so if I go back to the previous slide, this is the holy grail of extragalactic astrophysics. We have a dark matter backbone, and then we are getting galaxies into them. We know that we can connect these two through the simulations, but of course, in reality, what we have is the photons trying to establish that sort of trend. So the main thing is that the eternal connection is we have galaxies, stars, gas, and dust. We have light, and then we get the spectra. So the bottom line is that we're using those spectra to trying somehow to backtrack. For instance, this is a merger growth of a structure. So likewise, for stars, we would like to get something like the star formation histories. So I think this puts in a nice way what we're after. On the left, this is from the illustrious TNG simulation, but what you have on the left is the real thing. Basically, how many stars do you have of a given age and chemical composition? These are basically putting together your stellar particles from the simulation, and you see how many of them were formed. Some were formed earlier, later. They have maybe a more spread out distribution and metallicity, but all of them, each one of them will produce a spectrum. So normally from here to here, it's easy. The inverse problem is from here to here, it's much harder, and we are trying to get this. The two main parameters, the two main, if you want, values that we want to establish is the star formation history, how many stars are being formed as a function of time. So if you want, that would be the vertical side of this, and the chemical enrichment history, which would be the horizontal side, how the processes of enrichment are affecting the population. So that's the ultimate goal. We are trying to get this type of information. The way to go, all the time you may have seen these population synthesis modelings. This is just varying the age, and you have the range of spectra for two different metallicities just for illustration purposes. There are many other models, but all of them will be more or less similar. And what you have, as you can see here, you have a continuum and absorption lines. This is all coming from the stellar photospheres. This is coming from the surfaces of the stars that you're dealing with. You put them together according to a distribution of mass, according to a stellar evolutionary track. And then you say for a given age, if all the stars have exactly the same age and the same chemical composition, you come up with a spectrum, and that's the one you compare. You may combine them, producing composite stellar populations, but the bottom line is that you're trying to get this type of information. And we already know, for a long time, that there are substantial degeneracies, in the sense that you can obtain similar spectra if you vary a bit the age or if you vary a bit the metallicity. So that means those two parameters, you won't be able to separate them so well. We have degeneracies everywhere in science, of course. But before because I tend to be rather pessimistic, and my student is finishing now, and I think she was a bit depressed, like, oh my goodness, we cannot get anything. It's not so bad. I mean, there are lots of advances in the field by using these models. Even though there are degeneracies, you can still learn quite a lot about this. So for instance, major achievements, we already know that there is a well-established correlation between the stellar mass of a galaxy and the chemical composition, the metallicity, or the age. We already know that massive galaxies tend to be rather old, they tend to be rather metal rich, and this is purely coming from several aspects. One thing is the gravitational potential well traps the material that you have, the gas, so you can actually enrich the interstellar medium to a higher metallicity. And then you also have this interesting inverted hierarchy. You know that dark matter halos basically assemble in the opposite way as what you find in galaxies. You do find that the more massive galaxies tend to be older. So in a sense that the stellar populations were put in place at an earlier time. And this is coming from all the processes dealing with the gas physics, the way gas flows into the central parts of halos and triggers star formation. So these are things that are well known. And there's another plot here. You see the histograms, the star formation histories as a function of the mass of the galaxy. And you see that the most massive ones formed relatively early, with a relatively small tail, whereas when you go to lower mass galaxies, they are more spread out. And these are things that are well known. The details are more complex. Okay, the devil is always in the details, but at least we can actually get these types of results. We can even go one step further. We can even go into the subtle variations dealing with environment. Environment is much more complicated. So when I showed this previous figure, and that's something that deals with the second part of my talk, by the way, that I want to ingrain in your minds this idea that the most important parameter that drives the properties of stars in galaxies would be a local, in a sense that the mass of that galaxy is what controls whether this galaxy will be old or young, metal rich or metal poor. But then there's another effect, which is that galaxy, no matter how massive it is, can be in a cluster, it can be in a group, or it can be in the field, or it can be in a void. So that is environment. So this is over a much larger scale. Now we're talking scales possibly of order, I don't know, a megaparsec or so, or even higher. And what we end up finding is that when the galaxies tend to be the centrals, so at the same, you see the trend with respect to the local quantity, that's the velocity dispersion of the galaxy. So low mass galaxy, very massive galaxy. In all cases, the age goes up. But then when you segregate them according to whether these guys are centrals or satellites, you do find that the centrals in red here happen to be slightly younger. This is an environment effect. And we already know that this will be coming from the fact that if it's central, it's sitting at the very center of the dark matter halo. So you can have the gas flowing there, and you can have subsequent episodes of star formation. So then you're triggering later events that will produce younger ages. Whereas when you're a satellite, that's it. You have basically, you once you go into the galaxy, into the halo, sorry, you quench and you no longer form stars. So these are subtle details that are well known. Even here, this result that we produce, where you compare, let's say, two galaxies with exactly the same stellar mass, let's say, so they should have similar types of properties. But when one happens to be in a close pair close to a more massive galaxy, that happens to be older. There's this thing called a galactic conformity. So it's like the one that is around this galaxy tends to appear similar to the central one, so it appears older. Whereas when it's around another galaxy that has a lower mass, in principle, it appears younger. So these are results that it's not the focus of this talk. I just want to mention these things. You may know recently there has been an explosion of results from James Webb. Now, because we have decent data, I remember years ago we were playing with the slitless Grissom data of HST, And that was, I mean, I'm not going to show one here, but it was, in those days, I was showing that with pride. Like, my goodness, we have this spectrum of a galaxy at redshift 1.5, and it's absolutely pathetic compared to what you have now with NIRSpec. Now, with this spectra, you can already begin to see the problem of parameter space, in the sense that some of these galaxies appear to be very massive, indeed too massive for their redshift. You don't have enough cosmic time. You already know this business as well with the AGN, that you don't have enough time to grow the supermassive black hole to the mass you would expect if you're with the type of quasars that you see. So all this is the context I have. We already have done all these things. We have made a long advance in all these types of things, but now this is the standard approach, comparison with SPS, stellar population synthesis models. Can we do this in a different way? And the reason that now we can do it is because, as you know, we have lots of surveys. You have data, you can put together 1 million galaxies. So many years ago, people would say, well, it's my thesis, it's my galaxy. I have done one galaxy, and this is like NGC 4321, and this is my galaxy. And I have done, now, in a way, not so many people just concentrate on a single object because we have an enormous number of galaxies. So we can easily put a high quality set of data. So now that we have this, can we go for a data-driven approach? And what I emphasize is now I am not going, even though I may use the models, I'm not going to use them a priori. The only thing I'm going to say is, look, you have 1 million high-quality spectra. What does this type of spectra tell me? What type of information can I get from them? And there are various ways of approaching this. You can have the supervised or unsupervised machine learning algorithms. You may have seen so many of them. You have blind source separation. I will talk about this in a second. But these methods ultimately depend on the information encoded in the spectra. I mean, after all, keep in mind that all these machine learning methods, which have been working fantastically, the only thing they do is put numbers together. You have a sophisticated 1 million parameter model, and you're trying to fit these 1 million parameters so that you can get, for instance, the classification. Imagine you're classifying galaxies, early types or late types, or edge-on or face-on or whatever. What you do is you have this information, which are variations in numbers, and then the machine learning algorithm, what it does is just put together this in a highly sophisticated nonlinear way to say, look, if you combine those numbers, you end up getting this or this, for instance. So eventually, whatever you have information to begin with is what dominates and what determines how far you can go. And that's why I mentioned this entropy. If you have a system that where the information content is very small, no matter what you do, you don't get that much. And that's the point. And that's my concern, especially with spectra, because in that case, the entropy is actually, so the level of surprise is quite high. So we never get so much information. So just one slide to show you this blind source separation work. It has been done already for a long time. This, of course, has been applied to many other fields of what is a mathematics type of background, but it has been applied to many areas of science, and of course in astrophysics as well. The idea is very simple. You have your observations. Why? These observations are mixtures. So this is a matrix that mixes some fundamental sets of data. Imagine these are the simple stellar populations of a model. You mix them according to your mixing matrix, and perhaps you add a bit of noise. So there you go, it's a simple equation. And you can say, well, just I invert the equation. It's an inverse problem. I invert the equation, and I get the fundamental parameters from the observations if I can find a way of determining this W mixing matrix. So that's more or less the way these algorithms are trying to go through. They have different types of assumptions, but the essence is the same. So you can have principal component analysis, where the only thing you're doing is you're looking into the covariance of the information that you have. You can go further out, you go into the non-Gaussianity, so you go into the independent component analysis. You try to look for statistically independent data set. You have also the fission information matrix, artificial neural networks. I mean, I'm putting this because just to give you an idea of how many different things have been done. This is not so much the machine learning, deep learning that you're used to these days. I mean, these things, after all, I usually call these things shallow learning, in a sense that you don't need to have such a detailed analysis by going into so many parameters. You can, PCA, for instance, is a 0 parameter thing. So a variational autoencoder can easily have 1 million parameters. PCA has 0. Just get the covariance and diagonalize it, and that's what you get. So that's why I like this, because in a way, it's not so much of a black box as all these methods are. But of course, these methods have been there, and there have been lots of very, very interesting work that has been published on this direction. So for instance, as I mentioned, you can have a variational autoencoder. You have basically a network that tries to compress the information that you see into some so-called latent space. And then from the latent space, you're trying to recover what you were seeing. So basically, by having this tug of war between those two through the latent space, you may be able to learn or at least to do the classification. And these methods have been absolutely successful in many areas. I mean, Google and Facebook and all that, they're working so beautifully in many respects because they're applying these methods. When you do this to spectra, the result is not so impressive. So you can see, for instance, there are some papers here by Peter Melchior or by Portillo, where they compare variation autoencoders, let's say, with PCA or NMF, non-negative matrix factorization. And well, I mean, you get a better performance, that's fair enough. You find that most of your variation happens to be, I don't know, in the H alpha line. We already know that. So the results that you get from machine learning is whatever you knew. So whatever somebody from the 1970s would go, I told you so. This is something that happens. So it's fantastic, it works, but we're not gaining something new. And the other thing is these machine learning methods can be fantastic for classification, maybe for some type of regression, but interpretability is what I'm after. I'm trying to use these things as basically to teach me what's going on. Why are these galaxies looking the way they are? Why does the spectrum, why do these lines actually go the way they go? And interpretability is much harder. Okay. So part one, how much can we learn from galaxy spectra? A machine or ourselves? What type of things can we get from it? So this is something that we presented some time ago. And the idea is you can think of the spectrum in three different ways. The classic approach, a spectrum is a wavelength-dependent function. You have the flux as a function of wavelength. So you see how many photons do you get in a given beam, spectral beam. And that's what we're all doing all the time with the standard method, model fitting, etc. You can also say, look, a spectrum is nothing more than a multidimensional vector. So a spectrum would be, if you have, I don't know, 1,000 data points, you have a 1,000 dimensional vector. So different spectra will be different vectors in this space, and then you're trying to look for instance, clustering type of analysis, etc. This is the realm of multivariate analysis. This is where you can apply these things. And of course, another one that has not been explored so much is look at a spectrum as a probability distribution. So think of, rather than taking your CCD and taking your spectrum, imagine that you have a photon counter. And imagine it's like an X-ray type of photon counter where you can actually determine the energy, not only that whether you have one photon, but what energy you have. So you detect one at a time, bam, bam. So you ask yourself the question, the next photon is coming. What wavelength does it have? Then you have another one, and then another one, and then another one. So then you produce something that would be, rather than a spectrum, you produce a probability distribution from which you can determine the entropy. This is a concept done by already, the fundamental foundational work was done by Shannon in information theory. But the bottom line is entropy is a measure of surprise. Basically, this is entropy, the information entropy, not thermodynamic, but it's connected, of course. So we ask ourselves, what is the probability that the photon will have a given wavelength? If you already know this for sure, then you have a system with very low entropy. If you don't get the foggiest idea, it could come from anywhere, then you have the maximal entropy. So that's the idea. You use entropy as this type of measure. So you have this typical P log P, that's a way of defining it. And for instance, we can apply this to methods. These are population synthesis methods. Again, the same ones that you saw with the Bruchsal-Charlotte model. So let's say as a function of the age of the stellar populations, how much entropy do I have? And you can see it starts relatively low. It's still 0.97. I mean, the actual numbers you can renormalize, so you can change things. But the bottom line is that the entropy goes up. And these are two different metallicities. You can see the variations are not so important in any case. It's mainly that through age, the entropy goes up, which means through age, it becomes harder to learn from this. We already know. Those of you working on spectra for galaxies to deduce the properties of stellar populations can see that whenever you're dealing with a very old galaxy, it is much harder to find out things. Whereas when you have a young galaxy, because the variations of the parameters change so quickly, you can determine this much better. So yeah, we already knew that, that's fair enough. But the way it is done here is that the entropy is just one number. You have a spectrum, like a string of wavelength fluxes values for different wavelengths, and you just get a single number. It would be much more useful if we can separate this. So rather than taking all of them and combine them, so adding them in this integral, what you can do is take a small interval, a small spectral interval, and determine the entropy here and there and there and there. As you're doing this, you're producing an entropy spectrum, which is an interesting concept. So this is the entropy spectrum. Once more, it's doing exactly the same, but restricting yourself to a relatively narrow range. And it is an art. I mean, in our case, we just decided to go for for the general thing, it's about 100 angstrom. You're actually getting a fair amount of information. Typically, the spectra from galaxies are of a resolution of order 1 or 2 or 3 angstrom, so it's about 2,000 or so. And of course, information is connected with sort of the opposite, the complement of entropy. So this is a so-called negentropy, 1 minus that, in the sense that when you have more information, then this number actually more information means this number goes down, and then you have a higher number. So it's basically just another interpretation of your entropy. And you can see we have computed this once more on SSP models as a function of age, as you can see in the simulation here, well, the simple animation. And something that is very interesting, I mean, it's trivial in a way. We knew that. This is fair enough. But it's actually quite interesting to see that when you're doing this with an interval of order 100 angstrom, and you're just moving this around, you can already see that there are very specific parts of the spectrum where stuff is going on. Okay, anybody from, I don't know, the leak index group like Sandy Faber and company, would go, or Guy Worthy, would go, well, we knew that already. We knew that 40 years ago. So anything new that you're getting here? So that's fair enough. But it's interesting that purely from the information theory approach, this is the reason why we're using leak indices. This is the main reason, because you're getting all type of information from this area. So that's why we have this. And I emphasize, any numerical method, no matter how sophisticated, you can have a super sophisticated variation autoencoder, a transformer, you can have all crazy ideas that people deal with, all of them will have as input something like this. So I usually say, I remember when I started with this thing, I was wondering, well, why spectra don't work so well? And for instance, with audio files. So if you put an audio file of, I don't know, something from Bach, from Chopin, from Schubert, and even only the romantics, Schubert, Schumann, and Chopin, and you can actually separate them. Why? Because the information you have is much bigger. You have an audio clip for 10 seconds. It's much more than the number of bits of fluxes that you have in. This is like a one instant. I mean, you have 1,000 data points. If you have the sampling rate at, I don't know, 120 k's per second, that's absolutely nothing, no time. So that's why you don't have that much to play with, and that's why it becomes so much harder to do it. So when you're reading papers on these types of things on machine learning, you can see that this is something to be worried about. Now, what we did is apply the same thing rather than to the models. We applied this to Sloan data. And I'll just, well, this is a selection. You have to be careful that you have relatively high signal to noise, because otherwise noise can be a nightmare when you're dealing with these types of measurements. Restrict the velocity dispersion, redshift, etc. We have about 76,000 spectra. And I just wanted to show you that what you end up getting, you see, you can confront this. You have real stuff, real galaxies, and you have simulated galaxies. And it doesn't come as a surprise that the spectrum, the entropy spectrum that you get is very similar. After all, you have this large variation in the so-called 4,000 angstrom break region, quite a bit of it on the Balmer absorption, so in H delta, in H beta, H come as well with the G band, the NGB and FE, this is quite often used for metallicity indications, or the sodium line. H alpha is also there, but in principle, in real galaxies, you also have emission. Remember, I'm concentrating on stellar populations. Whenever you have gas, the diffuse gas can get ionized, and automatically you have an enormous line that will fill, especially this, so H alpha, sulfur 2, for instance, oxygen 3, the nitrogen 2s will be here as well. But you see now, the interesting bit is now we're seeing in a model, somehow model independent way, what type of information we can be getting from the data. So before we move on into a practical example, let me just show you another comparison. So you have 3 flavors of information. One is the real thing. This is what you want. You want to get the distribution of ages and metallicities if you want of your galaxy, what you get from a simulation. You have the real spectra, and somewhere in between you have the entropy. So what I was doing here is, if you compute through principal component analysis, you know that you separate the signal according to the variance. So you typically have the scree plot that starts at maximal variance and keeps on going down. If it goes down very quickly, the data are highly compressible. In a way, you don't have that much information. If the scree plot is flat, then you have much more information in the other components. I mean, in other words, if in the scree plot, the first component holds 99.99% of the variance, with one number, I can super compress the data and everything will be quite fine to within some small uncertainty. And you can see that when I'm doing this with spectra, the spectra are highly compressible. The real data is not so highly compressible, so it's much more complicated, more complex. And the entropy shows a position somewhere in between, basically a way in which you can still, you're not throwing, here what happens is basically by projecting onto this, into spectra, you kill lots of information. You really cannot get that much. So that's the bottom line there. So I'm going to stop this part of the talk on covariance. I mean, the idea is, after all, if you're doing things like PCA, for instance, you can see what's going on. Why is it so difficult to extract information from spectra? Here, this is the models. So BCO3 would be the stellar population models, and this is the real galaxies. And the covariance basically simply tells you how correlated these guys are. Basically, if you change one index, how much does the other index change? If they are highly correlated, you're not gaining any information. Your level of information is quite low. If they are highly uncorrelated, that's better, because then you can actually play with those differences. And you can see that in the case of simulations and in the case of the real data are highly correlated. Everything is highly correlated. That's why it becomes so difficult. You can see, I mean, here by construction, of course, the diagonal is 1, but then you see these parameters, even in the SDSS data, they have a fair amount of correlation. So playing with this type of information is the way to go, trying to see that. But the true level of degrees of freedom is low. And I'm mentioning this because those of you that are using spectral fitting, like PPXF or Starlight or any other concoction that people come up, it's a fantastic tool. But remember that the actual number of degrees of freedom is not what the numbers you're getting. So if you have a spectrum with 1,000 data points, you don't have 1,000 degrees of freedom. So your level of confidence is not the one you expect if you have 1,000 independent things. At least what you would have to do is use a covariance to get a proper chi-squared, for instance. So this is something that has to be taken into account and has not been done pretty much in most of the literature. And I'm just going to finish this part with just explaining a bit why is it so difficult. This is a typical spectrum of, let's say, a massive galaxy in the region around a sodium feature at close to near infrared at 0.8 microns. This is the same type of spectrum in a high resolution measurement for a single star. You can actually see, I mean, from here to here, the amount of information that you're absolutely butchering is blows your mind. I mean, you can see that you put one star, another star of different properties. This is just I put here, it's an M4 giant. So you have this star, but then you put another one. You put them together and you move them according to the motions that you have the kinematic kernel. Automatically, you end up with this. So how can you go from here to here? Maybe you cannot. Maybe the information is lost forever. So what I'm going to do now is show you a practical example on this effect. So far we have the general idea that we have the variance or we have the entropy. So something that doesn't use the models to begin with. So one thing we can do, and this is an interesting approach, this is a thesis of my student Zara Sharbaf. She's finishing as we speak. She's finishing by the end of November, moving to Barcelona. And what she was doing is trying to answer the following question. Can we use the covariance of the spectra of real data and of simulated data to gain information about why the models are working or are not working the way they are? So it's basically using this type of thing. Now you need to have two samples. You need to have a real sample and you need to have the simulated sample. So here, this is the first paper was doing a detailed analysis of the simulated sample. The different colors correspond to separating the galaxies into star forming in blue, AGN in green, and quiescent in red. We are simply using the standard BPT diagram. You use the line ratios from the emission lines from the gas, and you simply separate them that way. If you don't have any lines, it's quiescent. If you have strong, highly ionized material, then you go into an AGN. If your ionization level is lower, you have the star formation, and you can do this. And you see a 3D version of this is the latent space using PCA, restricting your analysis to only 3 components. So you take the first 3 with the highest variance. And yeah, I mean, you can see that the data are fine. So the data are these points, these dots, color dots that you have for the 3 cases. But I want here to show the effect of the models themselves. So what we do on top of that is these lines that you see, these curved lines, are actually the projections of synthetic models. Models for which we know the metallicity, we know the age. What we find, it's fair enough. It goes close to them, so that's okay. We already know that these models give reasonable fits. So that's no big deal. But one thing that is very important, remember I told you there is a degeneracy between age and metallicity. Now this is shown in a totally different way, because you can see the trajectories, those two, the solid line and the dashed line, correspond to age sequences at 2 different metallicities. And what you're finding is it's like you're simply changing the affine parameter. You know, you have a curve, and the only thing you're doing is you're sliding the other curve, which means that the degeneracy that you have between age and metallicity is enormous It's not just a cute thing that people have found, because if you make the object older or more metal rich, you end up getting similar things. At the level of the variance, the intrinsic variance down to the third component, you find this absolutely degenerate thing that basically the lines slide on top of one another, which is a bit disappointing in a way, as I said, because that means that degeneracy is very hard to break. So then what you do is, once you have characterized the Sloan data, the real galaxies, we go to the simulations and produce synthetic data that are comparable. Of course, now it gets much more complicated. You have to make sure that the galaxies are similar, otherwise you're going to get results that basically it's simply a systematic of the difference. And those of you who are working on simulations should be aware. I mean, I imagine all of you are aware, but it's actually quite uncanny. When you see the histogram of, let's say, something like Sloan, this is for star-forming galaxies, this is a function of the stellar mass. So you have a typical peak at around 10.5, and you have a tail going down to dwarfish type of galaxies. And you know that you run out of them because the survey is flux limited. You won't be able to observe anything because it's faint, so you won't be able to get it there. These are the Eagle, or the TNG for that matter, will be the same. This is the galaxies that you get from Eagle or TNG, and you see the opposite. That's a standard thing. We already know that the luminosity or the mass function of galaxies tend to be that way. You have a Schechter function in a way that it reduces exponentially at high mass, and you have quite a high power law type of behavior for the low mass. So you have to make sure that you're mass matching this properly, because otherwise you will get results coming from the fact that you're dealing with the different beasts. When we make the comparison to the first order, so for instance, here you can see that once more the same latent space from PCA down to the three components, the first three components. This is with Eagle, and this is with Sloan. And you can see that even though there are some differences, roughly speaking, we're populating similar parts of the spectrum, but you can already see, for instance, PC2, you see the histogram, it separates the star-forming quiescent AGN. Similarly, here you have a bit of a difference, and here you have also a substantial difference. Of course, trying to basically get the physics behind it is harder. You cannot really compare one by one on this latent space. So the way we're doing this is the following. We basically go, or if you want, let me just go back to the previous one. So we have a distribution of, let's say, component PC1. So you have a range of them. So you just select the ones with the lowest value and with the highest value. So in this blue histogram, star-forming galaxies, I'm selecting those with the lowest value of PC1, let's say the 25th percentile, and you have the 75th percentile up here. They are very different because of PCA. We don't know what that means, but at least we know that, which means we can stack them. We can put them together because we know that as far as covariance is concerned, these guys are somehow related. So when we do that analysis, we can now go to the models and make the comparison. And this is a comparison. This is the average age, average metallicity. And so these are once more comparing with population synthesis models of quiescent galaxies, of AGN galaxies and star forming. And we are basically comparing this against what you get in Eagle, for instance. So you can see, even though this one is covered a bit by the image, I mean, I guess we can put it here for the time being. You can already see that the star forming path is not so bad. I think it doesn't do so bad in terms of PCA. We separate into high and low PC1, Eagle and STSS. You find that the results are reasonable. So anybody, I mean, in our group at AISC, Claudio Dalla Vecchia, who is one of the experts on Eagle, goes like, that means feedback from star formation is actually okay. We can trust feedback from star formation, which is indeed the case. I think they're doing a reasonable job. When you go for AGN, it becomes harder. And as you will see in a second, dealing with AGN feedback is a much harder thing. You have to do it really by hand in ways that are not so well understood. And quiescent, because the quiescent are coming from these two avenues, star forming can quench, AGN can quench, you end up also with substantial differences. But now, if I show this for TNG, here, we have TNG, and I would say, this is even better. I compare TNG and Eagle. You can see once more, star formation is not too bad, but here you begin to see more substantial differences. And if anything, if I go back to the SDSS, here, AGN are actually mapped not so badly with Eagle, but the mapping with TNG is much harder. So the conclusion that we can get out of this is that even though we have seen many nice pictures of TNG galaxies and Eagle galaxies, and they look fantastic, and because they look like the real thing, they must be true. Well, not necessarily. And what you see is that when you look in detail, and this is at the level of covariance, we're going at the fundamental level of covariance, we actually see that something is going on regarding AGN, especially in TNG. So to try to answer that, this is the plot I wanted to show. I think this is quite a nice one. I think we ended up with a very interesting result. These are things that sometimes they are not shown so much in these papers because you can see, especially comparing one against the other. Normally, Eagle people do Eagle stuff, TNG people do TNG stuff, or Simba or whatever, and they don't talk to one another. But you can see here, the two main factors for quenching, the two reasons that a galaxy can stop forming stars is because star formation, basically you run out of gas somehow and then you stop the star formation, so you have the star formation rate, and the growth of the supermassive black hole, that's the AGN. So these two axes correspond basically to the main sources for feedback here. And you can see when we compare TNG and Eagle, Eagle actually, in my opinion, and I'm not an Eagle person, I'm not selling Eagle in any way, I'm totally independent here. I would say Eagle produced more of a general idea. There's not much correlation. You don't expect such a big correlation. Whereas in TNG, the correlation is uncanny. It's right there. If you have a strong star forming, you have a strong AGN, and it's always going to be there. So there's something going on, because you don't expect this type of thing. But the even more interesting plot is this one. So you know the way black holes are introduced in this simulation, these simulations don't have enough resolution to go into the details. So the only thing they do is, the galaxy grows, the dark matter halo grows, and when it reaches a threshold, you just put a seed black hole. You put it in the center, and then you let your hydrodynamics work. So if there's gas falling onto it, or if there are stars falling onto it, the code will actually keep track of the growth of the black hole. But the initial stage, the initial seeding of the black hole is coming through a sleight of hand. It's basically you just come up with an idea and say, put it there. And you can see when we compare Eagle and TNG, this is the seeding redshift. So you take all the galaxies in your sample within the sample that we have selected, mass matched, and you can see clearly Eagle seeds the black hole at substantially higher redshift. TNG seed at a later thing. Why? Well, mainly because their criterion for the threshold in the dark matter halo is higher. And you know that the universe grows from small to big. So if you have a higher dark matter halo, you need to wait for longer until you reach that threshold. So automatically you're going to wait for a little bit longer, and then you put your black hole. And here it's a similar thing with the distribution of the Eddington growth rate. This is basically the growth rate with respect to the Eddington limit. And you can once more see that in TNG, you have values that are closer to maximum value. So the way out, the way you interpret this data is that because you are actually forcing the black holes to be seeded at a later time, you're not quenching the way you should. And then suddenly you're like, oh, I'm running out of time. I really need to quench. And then they explode. They introduce feedback prescriptions that automatically kill the galaxy. They send the galaxy to kingdom come because they have to do it. You have to produce the number of quenched galaxies you see in the local universe. So once more, I'm not saying TNG is a bad simulation, but I'm saying these types of things have to be taken into account. And this is coming in our case. This is known from other types of analysis, but through the covariance analysis of the spectra, you automatically see these types of trends. So that's what I wanted to show in this part. Basically, that information, you can think of information as entropy or variance or things that are changing. This is fundamental because any of the algorithms that you use, even if it's the most sophisticated machine learning algorithm, will depend on how much of this variation is there. So we need to do that to understand the data. And what we have done is just follow the simple covariance approach based on PCA that allows us to compare real and simulated data, finding that to the lowest order, they appear okay. So I'm not saying that they really produce reasonable fits, but the problem there is with the AGN quenching and the mismatch with quiescent galaxies. These are things that have to be taken into account. And of course, the reason for it is subgrid physics, because after all, you don't have enough resolution. You cannot trace this physically. You put this by hand. You assume that when you have a higher value, automatically you have to somehow quench, but it is not coming out of, if you want, a set of equations that drive the evolution of the gas or the stellar component. So what I'm going to do now, I have some time, fantastic. I'm going to go to the second part of the talk, which is now no longer about entropy, but it's another thing that is unusual, that people perhaps don't think about so much, which is, we already know that there are scaling relations, and I'm going to show them, but the question is velocity dispersion the major driver of stellar populations over sub-galaxy scales? And I will explain this in a second. So in a different way, or maybe a clearer one, which scales dominate the process of star formation? The idea is the following. We know massive galaxies are old, low mass galaxies are young, have metal rich, metal poor, and all that. All these types of things have been obtained through integrated observations to whole galaxies. So, for instance, I think it's clearer if I show this here. There you go. I'll just put myself at the corner somewhere there. So, I like this because people, I mean, the younger ones in the audience, you will see, well, now there's only survey science. So there was astrophysics done in the 70s and even before. In those days, of course, you had to go and observe each one of them in a painstaking way, so your samples were actually low. But then what you find is when you're comparing properties such as the color of the galaxy and, let's say, the luminosity or the mass or the velocity dispersion, you find a substantial trend. This is the color magnitude relation that we already know, that we have explored in Sloan in minute detail. You have the Tully-Fisher relation. We already know that the rotation velocity of a disk galaxy correlates very strongly with the luminosity, and it's not a trivial thing. I mean, these are very few objects. When you put many more on the more recent data sets, you do find that this scatter is actually puts in trouble quite a number of theories, of ideas. And there's another one, which is a fundamental plane. When you put together for, let's say, early type galaxies or even galaxy clusters or even clusters of galaxies, velocity dispersion, the surface brightness, and the size, they don't live arbitrarily in three-dimensional space. They populate a plane. This is a projection in 2D, but they actually populate a plane called the fundamental plane. So it's very important. These scaling relations are telling us about what's going on with the galaxies. But I couldn't emphasize enough that when I'm talking about whatever I put here, or here, or here, or here, I'm talking about the whole galaxy. It's a global thing. So now the conclusion that you may end up getting is say, look, the properties that you find in these galaxies depend on the global property of the galaxy. So you consider the whole thing as a unit, in principle, you will get that sort of trend. So of course, you can try to answer that question. In the old days, as I said, the number of objects were small. Now we have the survey type of science in astrophysics, which is absolutely fantastic. We can do so many things with it. And you can, I usually say, sometimes when I say I'm working on slow data, people look at me like, my goodness, this is so last century. I mean, this is really old stuff. You can still get so many interesting things out of that. And we already have known this. I showed already another version of it, the age, mass, stellar mass relation in galaxies, or a correlation that you have on a plane of stellar mass versus radius. And if you plot this as a function of metallicity, you see a clear trend. This is the fantastic plot. I mean, it goes back to the model of Sandy Faber. This was done by my student, James Anthropo, but it's the same type of result, that you have a blue cloud, you have a green valley, and you have a red sequence that automatically is telling you have an evolutionary sequence. Because you have so many objects, you have hundreds of thousands of them, you can do this in minute detail. But once more, I'm talking about the global velocity. In this case, it's the central velocity, but measured within a fiber, so it's corresponding to the whole thing. I'm talking about the D4000 break measured there. We're talking about the radius of the galaxy, the mass of the galaxy. These are properties extended to the whole thing. So the next step would be trying to understand the scales. Once more, this has to do with the question, what type of scales drive or determine whether that part that you're observing happens to be metal rich or metal poor, or you have a old or a young star. So for instance, it's a simulation of, let's say, a giant molecular cloud, something relatively small. So over scales of order a parsec, you have stuff going on, lots and lots of interesting astrophysics going right there. And these are the birth sites of star formation. So after all, these have to be connected. But the scales I'm talking about are parsec. Now you can go to the next scale, the scale of a galaxy. So you have the typical galaxy and let's say the dark matter halo maybe. So now we're talking scales from the inner side, which would be of order, let's say 10 kiloparsec, even all the way to the halo, which could be, I don't know, 100 or so, or 200 kiloparsec. That's another scale you can consider. And you can also say, well, are the properties of these galaxies dependent on just the galaxy, but not so much the inner thing? And then finally, you can, of course, go all the way to environments. You can go basically to regions over halo scales, even environment scales. And we find, when we're doing the analysis with data, we find this trend is subdominant, but it is measurable. As I mentioned, the central satellite issue, the infall time, sometimes you're finding, for instance, when a galaxy, in principle, fell into a cluster at an earlier or later time, and there are connections. I mean, there's this projected phase space that I can tell you about if you're interested. So there are lots of interesting things that can be done. But the bottom line is that it seems like the dominant role happens to be here. And the question is, does it happen over very small scales or large scales? Now, the reason that we have those data presented over galaxy scales is simple. We only had in the past observations over galaxy scales for large surveys. I mean, for smaller ones, of course, people were doing detailed observations of a single giant molecular cloud or a single star-forming region. But we didn't have survey data. But that has changed, as you know, with IFU surveys. So we have SAMI, and we have MANGA, and we have all the many other Khalifa, Atlas 3D in the past, and Sauron. So now what you do is a galaxy is observed with several fibers, let's say, or an image slicer, whatever you do, but you have a spectrum at every point. Okay, now you do have spatial resolution. Now you can get your spectra not from the galaxy itself, but from a specific part of the galaxy. And the question that we have here is, once more, select the spaxels and forget about the galaxies they came from. So that's once more a crazy idea. Maybe say, well, I'm trying to see whether the correlations we find don't depend so much on the big galaxy, but they actually depend on local properties. And local reference variables could be the local velocity dispersion. I'm no longer talking about the velocity dispersion here. The velocity dispersion here is different. You can have different profiles. It could be isothermal, so it's more or less flat, or it could go down, it could flare and go up. You can have all these things there. And the question I'm asking is there a trend there? Radial distance, we have done this all the time. Every time you have a resolved galaxy, gradients, everybody's doing gradients. Why? Because gradients are telling you whether you have variation of the property when you go from the central part outward. The local stellar mass, so the stellar mass you measure in a single thing. Surface mass density or rotation. So just to show this in a different way, once more, we have this galaxy observed. This is the MANGA footprint. And what we do is basically what I usually like saying, you take all this information, you throw this to the floor and then scramble it. Say, look, I don't care. I don't care whether this comes from this galaxy. And then you take another one, and then you take another one, and you throw all of them on the floor. And now you pick them up according to the local property of each one. The local velocity dispersion, the local galactocentric distance, the local stellar mass, the local stellar mass surface density. And now the question is, can we actually get these types of properties scaling? You can do this very easily with, by the way, with MANGA. You may have been, if you haven't been working with this and you're interested, it's fantastic. It works. They have done a beautiful job. I mean, I usually, even though I have never been directly involved with Sloan, I sell them very highly because I think they have done a truly fantastic job. All the different flavors of SDSS are truly fantastic. So here you can get the data. So we selected carefully relatively high signal to noise, carefully that some galaxies were a bit problematic, etc. We come up with about 2,000 galaxies. And out of those 2,000 galaxies, I don't care whether I have 2,000. Now I know I have 1 million spaxels. So I'm only concerned about local properties. So I have 1 million spectra that correspond to local properties over a region that is, given the resolution, the PSF, if you want, of MANGA, could be of order 1 or 2 kiloparsecs. So it's not super high resolution, but we're talking about regions that are much smaller than the whole thing from a galaxy. And you can see, this is quite amazing. I mean, I was not expecting this, I must say. Usually when I'm doing these things, it's the same when we work with the IMF. I usually go, I'm going to show that this is not happening. And then, well, I see that it's happening, so well, whatever. So you see now, it clearly happens there. You see D4000, so the 4000 angstrom break, the H delta, and GFE prime. These are, if you want, any indicator that tells you what's going on with the stellar populations, whether it's old or young, metal rich, metal poor. Now I'm not concerned whether you're talking about an age or a metallicity. I even don't care. I only know that when the D4000 is high or low, it's telling me that this galaxy is special in the sense that maybe you have older stars or younger stars. And when you do this, you do find a true connection, a true correlation, especially with sigma. R, for those of you, if any of you here in the audience are working on gradients, you go like, poof, what's going on? I mean, something is happening. You can see when I use radial distance, I find actually the lowest correlation. So sometimes that's why when you see these people that I have been doing, myself included, plots on gradients, you do find that there's a huge amount of scatter. Well, the reason behind it is it's not so much that there's scatter intrinsically, it's mainly that the correlation is not there. So when you're trying to get radial gradients, doesn't work. My advice, go for velocity dispersion, local velocity dispersion instead. You can also have stellar mass surface density, or even this indicator of some value of energy. You have if you want the ordered and unordered velocity, so the sigma and the V. And you find that of all of them, this one wins over. We can show this in two different ways. You can show this either with absolute quantities. So here, each individual spaxel measures the sigma in kilometers per second. And here, this measures the sigma divided by the maximum value of sigma in each galaxy. So basically, are you close to the maximum value or close to the lower value? And here, the same, R divided by the effective radius
the mass divided by the maximum value of the mass in each parcel in a galaxy, etc. And you see that no matter how you look at this, it's always the sigma that wins the day. There's so much information here. I'm going quickly over it, but there's so much. So there are two ways that we handle this problem. One is the simplest one. I mean, just go for the simplest thing, of course, in all cases. Can we quantify somehow that this is better? Well, just go for the correlation coefficient. Of course, it's a linear thing. It's not going to work so well, but at least it gives you an idea. And when you go for the correlation coefficient, clearly you find that this guy, for instance, 4000 break or H delta MGFE, they are very strongly correlated when you're using sigma, local sigma. They are not correlated so well with distance. The sign is simply telling you that when you're going up or down, the populations may get older or younger. So that's not important. But it's mainly that those numbers are substantially smaller. With stellar mass, it is comparable. It's lower, but it is comparable. And the reason that I'm a bit, as you will see in a second, is that the way you measure this and the way you measure this is different. And this one carries more systematic. So perhaps the reason that these values are lower is not so much because in reality, this parameter is not so correlated. It's mainly because the measurement carries a higher, if you want, systematic uncertainty. So that's why you end up getting this. But the main result is this cross. Be careful with gradients, because after all, there's not so much of a correlation. A second way we did to try to go beyond the linear measurement of the parameter of the correlation coefficient is you just get all this data. You have a running value, let's say a running median as a function of sigma in this case. You go from the lowest to the highest. So the running median is this line in red, the running median. So at each point in sigma, you compute the standard deviation. So something could be super well defined around the median, or it could be all over the place. So this goes beyond the linear case. If it's non-linear, such as is here, then you can end up getting results. Once more, when you do these things, you find a substantially lower standard deviation for sigma, and of course, a much higher one, as you can see directly. I mean, this you don't need statistics for that. You can see this straight out of the plots. So I don't want to go too much over time. So I just want to put a couple of slides more, and I will stop. This is a fundamental thing that we are not used so much to it in science in general. I mean, we have it all the time, but we never think about it. Correlation is not causation. I mean, some people think about it, of course, but not so much. And you can see that especially the mathematicians are much more careful about these things. You need to assess whether the trends you find are pure correlations because you have something else. And you know that there are typical examples where you have crazy things where you're trying to make correlation causation and you get an absolutely crazy idea. So for instance, if the typical one is in the summertime, more people buy ice cream, but in the summertime also more people drown at sea. So the correlation is if you eat more ice cream, you will drown at sea. So you cannot use those two variables. We know they are connected, but they are not. You cannot have the causation. The way to solve this is highly non-trivial. It's not. I don't think there's a unique solution to this. So one of the things we did is simplify this. Let's target two test variables: velocity dispersion and stellar mass. Both can be the driver, so to speak, the main one that controls the properties of the stellar populations. And what I'm doing in these plots is we have the whole sample again, here done as a function of velocity dispersion and here as a function of stellar mass. And what I do is I separate once more the lowest and the highest percentile, 25th and 75th percentile. And you can see this plot in the top is trivial. I simply go the lowest and the highest at fixed velocity dispersion. And you can see that when you compare them doing sigma or doing stellar mass, the largest variation in D4000 in H delta in any parameter happens to be when you are actually considering variations in sigma, regardless of the stellar mass. In a way, this is automatically telling you that at least the variable that is more strongly driving this is the velocity dispersion. I haven't still shown causation. I haven't found causation anyway. But the next bit that we can do is the following. And let's think about it. How do you measure velocity dispersion? You take a spectrum. You have another reference spectrum. Let's say you take a star, a velocity standard, and you basically blur it somehow in a different way until you find a match. So automatically, out of a single spectrum, you can have a highly detailed, high-quality measure of velocity dispersion regardless. So your systematic is very low. How do you measure stellar mass? You take the photometry, you compare with population synthesis models, you derive a stellar to luminosity ratio, you go to the photometry again, and you convert your light into mass. So you have a huge amount of systematic there. So that's why you have more error. So one way to try to solve this, and as I say, we haven't solved it, but at least it was a cute example, is, okay, now we know that sigma can be measured better because the actual measurement can be done in a better way. So let's by hand let's actually make sigma as bad as stellar mass. Let's add noise by hand. And let's keep on adding noise. This capital delta is actually the amount of noise that I'm adding to my velocity dispersion. And I'm comparing either the correlation coefficient, so the first method I mentioned, or the standard deviation about the running median. And this is the original value. As I keep on adding noise, of course, this will go up. You have a higher deviation or you will have a lower correlation. And when you're hitting the value that you get for stellar mass, which is this horizontal blue line, you find something very interesting. If you use D4000, if you use H delta, if you use correlation coefficient, if you use standard deviation, in all cases, the amount of noise that you need in order to plane basically sigma and ns on equal basis is you need an extra error of order 0.2x. It's at the borderline. So some people may go, that might be okay. But if you consider that this is way too high, your conclusion would be that sigma is the causating variable. And ms happens to be connected in a sense that the higher velocity dispersion in principle will give you a higher sigma. So that's where you have the trend. So that's the conclusion that I ended up getting. So I will just finish with one slide and I'm done. And that was in a way just to show you that these properties depend locally, but it is not the whole story. Everything, of course, is much more complicated. So for instance, here, going back to the BPT diagram, we separate the galaxies, not the spaxels, the galaxies themselves into whether they are quiescent, AGN, or star forming. And then what I do is I only consider the spaxels in the outer region so that I'm not affected by the classification, of course, is dependent on this. So whatever you get will be truly correlated. So I simply go to the outer parts of these galaxies that have been classified in the central region as quiescent, AGN, or star forming, here, as you can see. And you do find that the variations that you get, the trends, mostly affect how much of this distribution is shown, but it doesn't change. It doesn't change the shape. It simply says that when you have a quiescent galaxy, even in the outer regions, you tend to have more of the older, if you want, values, so high 4000 break. Likewise for star forming. So it's interesting that you have also a non-trivial connection with the global aspect. That's why there's some paper by Anna Galazzi and Stefano Civetti, you may know them. They have done fantastic work. And with Khalifa, they define, you have global variables, you have local variables, you can call them glocal variables because you have in a way a bit of both. So I hope I have convinced you that at least this is something interesting and worth scratching your head about. So I'm going to, in this second part of the talk, you can see we have found a very strong correlation between the stellar population indicators and local regions over a kiloparsec, regardless of galaxy mass size morphology. Once more, I emphasize, even if you're dealing with an elliptical or with a disk or with any irregular galaxy, as long as the local velocity dispersion is the way it is, you can already derive to a reasonably good extent the properties of the stellar populations. The bivariate comparison suggests local velocity dispersion as the main driver, and the way we can paint this picture is you have a perturbative scale in the sense that when you to the lowest order, to the most important result would be over kiloparsec scales. Then you have an effect that would be lower over galaxy scales, and then you have the next one, which would be halo environment. So I'll stop there. Evkaristo. Thank you.
Ignacio, this is not what we normally do. This is rather advanced, at least for me. I don't know, some of the students here may be more familiar. Questions? Okay, yeah. Okay.
So thank you, Ignacio. Amazing stuff and a lot of food for thought. So I have two questions, one for the first part and then one for the second part. For the first part, when you analyze the TMG and the Eagle data, so you use spectra. Okay. So how much do your results depend on the prescriptions that they have put into the ionizing spectrum of the AGN, for example, and how this affects the gas? Because what you're measuring is the response of the gas to the ionizing spectrum of the AGN. And each simulation has its own prescription, both for the gas, for the ionization parameter, and so on. So how much do your results depend on?
That's a very good question. And this is one of the things that we were very much concerned about. So what we're doing, first of all, the simulated galaxies we produce only concern the stellar populations. We don't introduce any gas component. We don't even introduce dust, 0th order. So you can already see, and there could be something here. The second aspect is whenever you're dealing with the gas components, for instance, to consider whether this galaxy is classified as an AGN, we didn't do that. And I think it's the next step. What we simply said is, look, if the lambda, the growth rate of the supermassive black hole is high enough, automatically we consider that to be typical to the AGNs we consider, which in our case happen to be this type 4, which is strong AGN. So that's why we avoid things that are in between. For star forming, likewise, if you have a star formation rate that is reasonably high, automatically it's your BPT flag 1, which is strong star forming. And quiescent, likewise. So it's a very good point. If you want to do this properly, like in more detail, then you would have to do exactly what you're doing.
So it's not actually BPTs, it's like mock BPT.
It's mock BPT,
Okay,
totally. Yeah,
okay,
yeah,
okay.
absolutely. The second thing I wanted to mention, now that you had this nice question, is you know, you can imagine when we did the analysis with Sloan, because the correlation is stronger with velocity dispersion, we used velocity dispersion as the main parameter. Now we went to TNG and ECO, and as you know, because the velocity dispersion is derived from stellar particles, the values, I mean, it's all over the place. It's really bad. So we said, okay, we have to use stellar ones. So when you make the comparisons, you always have to adapt to the best that you have. But our next step is, for instance, there are these models by Michaela Hirschman, where she puts the gas component and you can have lines, and then we can do exactly the same thing.
Exactly.
It will be very interesting.
Yeah.
You had a
Yeah, can I ask the second question?
Of course.
So the second question is about your results between the T4000, for example, and the velocity dispersion, which is very, very interesting. So I'm wondering, have you explored whether you have, what is the degree of similarity of this correlation between, for example, star-forming galaxies or early type galaxies? Because by looking at the plot, I would expect that the top part of the plot, where you have a high D4000, a high velocity dispersion, will be driven by the early type galaxies, and the lower left corner will be driven by the star-forming galaxies.
Yep. It's a very good point. We do have. Let me see if I can show you. Let's see if I can go. So if I stop here, let me see if you can see this one. So for instance, this plot. Well, this is similar to the one we have, but we separated here in the sample according to, this is the D4000 high value and low, but let me just, possibly this figure, which is, it's similar to the one I presented, but we have a different way of separating us. Red sequence, green value, blue cloud. So you can see it in a better way. That when a galaxy has considered to be a red sequence and you put all the spaxels in, you can see these guys and these guys who have the blue cloud possibly coming from the outer part of that galaxy. So you can see how that builds in.
Right.
And clearly that's one way of,
Okay, so it's effectively galaxy evolution that drives even the sub-galactic series.
True.
Yeah. Okay.
So that's why in a way, that's what I said, that in a way you have to the lowest order, the local properties there, but you do have differences here, that if the object happens to be, as you say, an early type of object or a disk galaxy, then you will find a different distribution.
Yeah. Nice, very nice.
Thank you.
Yes.
Hi, thank you, very nice talk. I have maybe a question for the first part of the entropy analysis as you presented. So, would you say that this method can be used in order to define, let's say, new diagnostics, for example, in like for future selection in terms of machine learning? Because, okay, the spectra that you show as an example, yes, we expect that specific lines will show the highest variations. But there are other problems where we have no idea about which features we should use, either in spectra or maybe in images for galaxy classification, for example, morphological classification. So I was thinking if this method with the entropy and looking for the variations could be used in such kind of problem.
Absolutely. I mean, I think that's one of the ideas we're playing with is, for instance, you can use this as a way of weighting your data. You have your data, so you give more weight to regions where there's more entropy happening. So in principle, that's a way of doing it. It is not trivial, but in principle, you would say wherever you have more information happening, then you give more weight. So all this machine learning, and if you, for instance, have an autoencoder, automatically, if you filter them through these types of ideas where you're putting the weights, in principle, you should be able to produce these results. There are other methods that people are trying to get. For instance, even when you go to the latent space, you can apply PCA and separate the components and try to give more importance to the ones where the variance is higher, and then you just go back to your images. So there's a whole world of things that could be done, but it's a very good point. I think this is one of the uses of entropy, or the variance or information content would be to guide these algorithms. And I'm emphasizing that's a good point. Something I wanted to say that I didn't mention. For instance, you know that people find that when you look at spectra, some special lines are gravity sensitive. They depend on whether you have giant stars or you have dwarf stars. And this is the way that we have been obtaining things like this IMF trend, that you have a more bottom-heavy IMF in the central parts of massive galaxies. So there are very specific lines. And when you look at the variation, it's 1%. So of course, if you're feeding blindly a machine learning method, 1% will be nothing. It will go to the main thing. So perhaps this is also that you filter this somehow. You have that additional information. You say, as far as the IMF is concerned, the entropy is actually here more important, so you give more weight. So there's a whole avenue of research to be done there, because sometimes I think people apply these machine learning methods very much in a blind way. So you just put them in, put them out, see, close your eyes and hope for the best, and let's see what comes out. And you see, when you do this properly, you may end up getting basically reaping the benefits of having such a sophisticated method. But you really need to modulate those numbers in this way. So using this type of information would be important. Yeah, good question. Yeah.
Let me ask the last question. These are very sophisticated methods. Do you see community going in this direction in the future? Or it's a must, you think? Because in the past, this is my galaxy, this is my spectrum, I take all the information from it, and so on. But now, with thousands of galaxies, you have to be more automated and yes. Do you see the community going in this direction in the future?
At least the way I would see it, the advantage of having this type of ideas is that at least people start thinking about how careful you have to be when you're using this method. So machine learning methods, now people are applying it all over the place. I mean, sometimes too much of it. Sometimes they're basically saying, look, because the simulations show this, the real galaxies show that. And you see that the difference between the statistical behavior simulations and real data is enormous. So if you blindly apply these things, you won't get the results you want. So these are the types of things that I would say will help. Implementing a method itself, I don't know. I think it's very tough because, as I said from the beginning, when my student is also very, very pessimistic as well, in the sense of saying it is so hard because there's such a high level of entanglement that it is difficult. But in principle, it's an advance in the sense that whenever we apply these statistics-based models, in whichever way, multivariate analysis, machine learning, we have to take all these values into account.
Okay, well, let's thank Ignacio again.